my name is İsmayılova, and today I will present my internship work on comparing quantization and SE compression in federated learning. I did this internship at FEMTO-ST under the supervision of Professor Raphael Couturier, and the project is about reducing communication costs in federated learning while keeping the model accuracy stable. I will first introduce federated learning communication problem, then I will explain the two compression methods I compared, quantization and SC3, and after that I will describe the experimental setup, show the main results, briefly mention exploratory runs, and finish the discussion and conclusions. Federated learning trains a shared model across several clients without collecting their raw data in one place. In each round, the server sends the current model to clients, and clients train locally, then send model information back to the server. The server aggregates this information into a new global model. This is useful for privacy and distributed data, but it creates a communication bottleneck. The model is exchanged many times, so the total number of transmitted bytes can become very large. In my project, I focus on client-to-server direction. After local training, clients send their trained model parameters back to the server, and I apply compression to these transmitted parameters. The question is, can we reduce communication while keeping accuracy close to the floating point 32 baseline? I compared two compression families. The first one is uniform quantization. Instead of sending each parameter as 32-bit floating point value, quantization maps values to fewer integer levels. For example, 8-bit quantization uses 8 bits instead of 32, so the expected reduction is about 4 times. The advantage is that it is fast and simple. The risk is that the bit width is too small. The constructed weights can become too distorted. The second method is SC3. SC3 is an error-bounded lossy compressor. Instead of choosing a bit width, we choose an error-bound epsilon, and after the compression, each value must stay within this bound of epsilon. So quantization is controlled by bit width, while SC3 is controlled by error tolerance. I tested 8-bit and 4-bit quantization and SC with error bound 0.001 and 0.01. This slide shows the training loop. The server starts with a global model, then client receives it and trains locally. After training, client has a local model. This model is compressed and decompressed, then sent to the server. The server aggregates the reconstructed parameters. So I compress model weights, not raw gradients. This is important because many papers focus on gradient compression, but my implementation keeps the federated average aggregation unchanged. The experiments use Flower with race stimulation. Flower provides a federated learning structure, including client, server, and fed average aggregation. Ray allows clients to be simulated on one single machine. The dataset is CFAR10 and the model is ResNet 20. I used 10 simulated clients. The data is split in non-IID using Dirichlet distribution with alpha equal to 0.5. This means the clients do not have all the same data distribution, which is closer to real federated learning case in real life. Each client trains locally for 2 epochs, and the experiments runs up to 200 rounds. The compression is applied after local training before the client sends model parameters back to the server. The server still performs standard federated average. The main comparison includes 5 runs. Floating point 32 is the uncompressed baseline, 8-bit quantization is the practical quantization baseline, 4-bit quantization tests a more aggressive low-bit setting, SC with error bound 0.001 is the conservative error bound setting, SC3 with error bound 0.01 is the more aggressive SC setting. These runs answer how quantization and SC3 behave under the same federated learning setup. Here we can see the accuracy behavior. 32 reaches about 87.7% peak accuracy. 8-bit quantization reaches about 87.9%, so it preserves FP's 32 level accuracy. SC with error bound 0.001 also preserves accuracy, reaching about 88.1%. SC3 with error bound 0.01 still trains, but settles lower, around 84.2%. So it gives more compression but introduces an accuracy cost. 4-bit quantization collapses and reaches only about 21.5% peak accuracy. So 8-bit quantization and SC3 with error bound 0.001 are safe in this setup, and SC3 epsilon equal to 0.01 is a trade-off, and 4-bit quantization is too aggressive. Now looking at communication, floating point 32 has a compression ratio of 1x. 8-bit quantization then gives about 4 times compression as expected. SZ with error bound 0.001 gives about 4.2 times, so slightly better than 8-point quantization while keeping similar accuracy. SZ3 with error bound 0.01 gives about 7.4 times compression, but with the accuracy drop shown below. 4-bit quantization gives high compression too, but it's not used because the model fails to train. So the important point is that communication savings must be judged together with the accuracy. This table summarizes the main results. 8-bit quantization is the strongest practical baseline. It is fast, simple, and gives 4 times compression without accuracy loss. SZ3 with error bound 0.001 is competitive. It keeps the same accuracy level and gives slightly higher compression ratio, but with higher overhead. SZ3 with error bound 0.01 gives much stronger compression, 7.4 times, but loses around 4 accuracy points. 4-bit quantization gives high compression, but accuracy collapses. So there is no single universal winner. The best method depends on whether the priority is simplicity, accuracy, or stronger compression. I also tested different exploratory methods. First, round-based SC schedules. These start with a tight error bound and relax it later during training as the model learns more at the beginning of the training process and later epochs it plateaus, so we can compress more aggressively there. Second is USNR-RMS, which chooses the SC error bound from the magnitude of the local update. Third, a hybrid method where SC3 is used for larger tensors and 8-bit quantization for smaller tensors. These methods helped explore the design space, but they did not clearly improve over the main baselines. This table compares main and exploratory methods. The strongest accuracy still comes from main methods SC error bound 0.001, 8-bit quantization, and floating point 32. The scheduled methods reach higher compression, around 6.7 to 6.8 times, but with lower accuracy. The hybrid methods preserves accuracy, but its ratio stays close to 8-bit quantization, so there is no real gain. USNR RMS is stable, but it has lower compression and higher overhead, so it is totally useless. So more adaptive methods were not automatically better in this setup. The results make sense because compression introduces reconstruction error. 8-bit quantization works because the error is small enough for federated average to remain stable. 4-bit quantization fails because 16 levels are too coarse for this setup. SC3 is useful because error bound gives direct control over the reconstruction error. With error bound 0.001, the error is small enough to preserve accuracy. With 0.01, communication improves, but accuracy decreases. And the main limitations are that I used one dataset, one model, and 10 fully participating simulating clients. I also compressed full model weights, not updates, and did not use error feedback. So these results are specific to this setup and may not be widely applicable to all federated learning systems. To conclude, the compression can reduce federated learning communication without necessarily hurting accuracy. 8-bit quantization is the most practical method tested so far. It gives 4 times compression, is fast, and preserves accuracy. SC compression with error bound 0.01 is also competitive, with similar accuracy and slightly better compression. SC3 with error bound 0.01 gives stronger compression but loses accuracy. Future work should test more clients, partial participation, larger models, update compression, and error feedback. The final takeaway is that communication-efficient federated learning is the balance between accuracy, bytes, and overhead. Thank you.